A transformer is a conversion machine built from copper and iron, materials that impose physical limits on efficiency. While power transfer is often calculated as an ideal exchange, the actual operation of a transformer involves a continuous, measurable drain on the electrical grid. This is the full phasor model for a transformer under a lagging inductive load. Each vector tracks a specific physical event, from core magnetization to internal winding drops, providing a complete accounting of the system's energy state. These vectors quantify the resistance and magnetic leakage inherent to the machine's design. They map the behavior of miles of tightly coiled copper wire and the massive laminated iron core that couples the circuits together. On this equivalent circuit, we see those constraints categorized. R1 and X1 represent the primary winding's series resistance and leakage reactance, while R2 and X2 track the same forces on the secondary side. Between these windings sits a shunt excitation branch. Because the iron core requires constant magnetization to induce a current, a transformer consumes power even when the secondary circuit is completely open and idle. To synchronize the primary and secondary behaviors, we need a single magnetic baseline. We establish the mutual core flux as our horizontal reference, serving as the anchor for every other vector in the system. By tracking the exact phase angles and lengths of these phasors, engineers can predict exactly how internal impedance will warp the output voltage before it ever leaves the substation. The core flux remains the constant reference point. Faraday's law dictates induced EMF lags flux by 90 degrees, so primary E1 and secondary E2 point straight down. To maintain equilibrium, primary voltage V1 counters E1, extending vertically upward. When the secondary is disconnected, the primary still draws a small current to sustain the magnetic field. This is the no-load current, or I0. In an ideal circuit, this current would be purely reactive, existing only to maintain the flux. We call this the magnetizing component, IM. This diagram reveals that the actual no-load current is the resultant of two orthogonal vectors, the magnetizing component, IM, in phase with the flux, and the active working component, IW, which is in phase with the applied voltage. The working component represents power required to overcome core iron losses. This energy dissipates as heat through hysteresis and eddy currents within the laminations. The vector sum of IM and IW gives us the total no-load current, I0. Its position creates the no-load power factor angle, phi0, indicating the baseline efficiency of the transformer. Even at rest, the geometry of the system is shifted. No load does not mean zero loss. The physical properties of the core ensure the system is consuming energy the moment it is energized. We transition to a loaded state by connecting an inductive device, such as an industrial motor, to the secondary terminals. Because the load is inductive, the secondary current, I2, exhibits a phase lag relative to the induced secondary voltage, E2. We plot this current at a specific lagging angle, phi2. Terminal voltage V2 remains after subtracting secondary internal drops. Copper resistance creates a resistive drop, I2R2, in phase with current. Leakage flux adds a reactive drop, I2X2, at 90 degrees. Subtracting these from the induced EMF yields actual terminal voltage V2. The secondary impedance functions as an internal voltage tax. The power available to the load is now visibly reduced in magnitude and shifted in phase compared to the original induced voltage. When the secondary draws current, it produces a demagnetizing flux. According to Lenz's law, the primary side must immediately draw a corresponding load current to neutralize this effect and maintain core magnetization. This reaction is mapped as the primary load component, I2', drawn 180 degrees opposite to secondary current. The phasor sum of no load current and this component gives total primary current I1. With primary current established, we calculate total grid voltage required. Plotting the primary resistive drop parallel to I1 and reactive drop at 90 degrees accounts for copper and leakage losses. Summing these yields total applied voltage V1 and the primary power factor angle phi1. The primary source must over-deliver both voltage and current to compensate for the cumulative losses in both the copper windings and the magnetic core. The power factor of the load is the master variable dictating the system's entire geometry. With an inductive load, phase angles subtract directly, significantly decreasing terminal voltage. If purely resistive, current and voltage align, reducing subtraction. With a capacitive load, current leads. The reactive drop swings upward, adding to the induced EMF, making terminal voltage longer, a condition called voltage rise. The phasor diagram acts as a strict visual ledger, helping engineers determine exactly how much voltage is required at the primary terminals to maintain stability at the load, regardless of whether the equipment is inductive or capacitive. By mapping these vectors, we visualize the invisible magnetic forces dictating the flow of electricity, ensuring modern grid stability through geometric precision.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.